Welcome to Empowered Learning. This is the third video in the video series on polar coordinates and equations. So in this video, what we're actually going to do is to see how we can take a polar equation and convert it to a rectangular one and vice versa. If you've watched the two previous videos that I have, then one of the things that you may have picked up is how we parametrically define a polar coordinate in terms of this equation here and this equation here, that x is equal to r cosine theta and y is equal to r sine theta. And of course, r is square root of the sum of the squares of the x and y coordinates in rectangular form. So we're going to use that to help us to be able to figure out in these first set of examples here an equivalent rectangular equation for the polar equations that will be given to us. Now, before we begin these examples, I kind of want to explain why we're doing this. So if you're watching this video, then more than likely you have taken a basic algebra course or advanced algebra course, or maybe even a pre-cal before, or maybe that's what you're in now. The point that I'm trying to get at is that in a basic college algebra or pre-cal course, one of the main things that you should pick up in those courses is how to graph basic functions. So for instance, you should have picked up in that course that y is equal to x squared is a graph that basically looks like a U. You know that square root of x is a function that kind of looks like this. Okay? And so one of the key things is being able to memorize what certain graphs look like for certain functions. Well, we're kind of carrying that idea over into polar coordinates and polar equations. And we're going to see that in the fourth video, when we learn how to graph polar equations, that we have our own collection of graphs that kind of go along with that particular concept of a polar equation. And of course, for the most part, most of these equations are not going to be functions. So we're going to need, well, I'm not going to say we're going to need. I think, in my opinion, it is advantageous for you to memorize what the basic profile of what some of the more common or standard polar equations look like, and use tricks, just like how we use transformations with algebraic functions like x squared and square root of x. We could use tricks to kind of figure out, well, how is that particular profile going to be orientated on my graph, okay? Now, how all that comes into play here is that what we are doing is sort of the brute force way of being able to figure out, well, if I wanted to graph this polar equation and I didn't know anything about polar graphs, I could convert my polar equation into a rectangular one, and then if necessary, I could just plot a bunch of points, XY points, to be able to figure out what the graph looks like. So if I made a list of x values, I would calculate it, find the corresponding y values, and just plot the graph that way. And so with us taking the polar equations and converting them into rectangular equations, which is everything in terms of x and y, we will now have the ability to do that. In this video, we're not going to focus on graphing these equations, but we are going to focus on figuring out what the rectangular version equivalent of these equations are. But the reason why we're doing it is it allows us to be able to see, now I know what this is in a rectangular equation, and if I just wanted to plot some points, I could actually do it. So that's why we're doing this. All right, so let's go ahead and jump right into our first example here. So we see here that r is equal to 3 sine theta, and we want to figure out what the equivalent rectangular equation would be for this. Now, note that we have a sine theta here, okay? And so we know that y is equal to r sine theta, but we also know that we could algebraically manipulate that equation to find out what sine theta is just in terms of y and r, okay? So here I could come and say this is the same as 3 times y divided by r, or just 3y divided by r like that, okay? Now, that doesn't necessarily help me get rid of what r is yet, but if I kind of collect what I have, notice that I could multiply both sides here by r now, okay? And if I did that, then this side would be multiplied by r, and I could square this. And what I would have is r squared is just equal to 3y. Now, that's good because we know that since r is square root of x squared plus y squared, if we squared that, what we would get is just x squared plus y squared. And so now if we have that, we technically at this point have our equation here in rectangular form, okay? Now, the thing with this is that although we have this in rectangular form, it's probably not something that is readily recognizable. So one of the things that we do see here is that this could possibly be an equation of a circle. And we know that because the coefficients on the x squared and the y squared are the same. And thus, what we could do is use completing the square technique to help us be able to get this into the standard form of an equation of a circle that most of us are familiar with here if you've studied circles before. And so that's what I'm going to do here, because once I convert this and try to get it in this standard form of an equation of a circle, I'll know exactly how to graph this if I need to, okay? All right, so to do what we need to do to use the completing the square, I need to subtract both sides by 3y, which will end up being this. And so I know for these last two terms, I need to kind of rewrite everything here. So where I'm going to need a number here to make this expression here be a perfect square. And whatever that number is, this is going to be the same thing over here. So of course, for completing the square, we know what we have to do here is take that middle number 3 here, divided by 2, and then square it. And that will be the same exact thing that we need to do here. And so what that ends up being is 9/4. So when we go clean this up here, this will just be x squared plus y squared minus 3y plus 9/4 equals 9/4. Okay. And note here that y squared minus 3y plus 9/4, that is going to factor into y minus 3/2 quantity squared. And this 9/4, you could keep it that way, or you could rewrite it as 3/2 quantity squared. And so in this form, we not only have it in rectangular form, but we realize that this is a circle where its center is at the point 0, 3/2, or 0, 1.5, and that its radius is 3/2, or 1.5. So we could take that information and actually graph this equation if we wanted to. All right, so let's move on to our next example. All right, so for our next example here, we see that we have r is equal to 3 secant theta. Now, the first thing we recognize is that we know that secant is the reciprocal of cosine, so I could rewrite this as 3 divided by cosine. Okay. The next thing I remember here is that if x is equal to r cosine theta, then what that implies here is that cosine of theta is equal to x divided by r. So I could rewrite this way. And using what we know about complex fractions here, this would be 3 over 1 plus, so we change from division to multiplication, and then we flip this bottom fraction here. So this would just be 3r divided by x. So therefore, what we have at this point is r is equal to 3r divided by x. And notice at this point that we have an r on both sides. So if I was to multiply both sides by 1 over r, or put another way, divide both sides by r, then these r's would reduce to 1. And what I would have left is 1 is equal to 3 divided by x. Now, if we multiplied both sides by x, then that's essentially telling us that x is equal to 3. And what we see here is that r equals to 3 secant theta. That's just another way of expressing the Cartesian or rectangular vertical line x is equal to 3. Okay. And so that's pretty much it for that. Now, I know that in doing this, there are a few minor details that I skipped, and I'm going to talk about that now just to make sure that mathematically all this is correct. Okay. So note here that we know secant is never going to equal 0. Okay. And so since secant is never going to equal 0 for any theta in this domain, I'm allowed to actually divide both sides of that equation by r that I did up here earlier. Okay. So to put that another way, here, this notice here that this r actually represents 3 secant theta. Okay. And so the point that I'm trying to make here is that since secant can't equal 0, then it means that r can't equal 0 either. And so since r not able to be equal to 0 is something that's a reality for us, I can actually go and divide both sides of this equation that I had here by r, and it actually be something I can legally do. If there was a situation where r could equal 0, then I wouldn't be able to do what I just did here. Okay, I would have to find another way to be able to try to figure out how to solve this equation. But since I knew r could not be equal to 0, I could easily divide by r and everything's okay. So I just want to make sure that we illuminated that before we move on, because a lot of people do the whole thing of dividing by r and they just kind of take it for granted. But it is something that you do need to pay attention to make sure that you actually can do it before you do it. All right, so in this next example, we see that we have the polar equation theta is just equal to pi over 4. Okay, so this represents essentially all the points that are on the polar axis pi over 4. So just to kind of graph that so you can kind of get a picture of what that looks like here. Let's say this is a polar plane here, and we want to draw what that might look like. So any point that's on this brown line here would be what this equation represents. Now, notice that this particular equation here, and I'm assuming that it's going through the center here, this looks like a line with a positive slope with 0 as its x-intercept. And we're going to see that whenever we translate this, is actually going to make sense. Now, note here that since we know that sine of pi over 4, which in this case is 1 divided by square root of 2, is also equal to cosine pi over 4, then in terms of what we know about this conversion here, remember here that x is r cosine theta, y is r sine theta, okay? Which for us means that x divided by r is cosine theta, and y divided by r is sine theta. And so what we're saying is that at the same angle, pi over 4, sine and cosine are equal. So what this means is that x divided by r has to be equal to y divided by r. Okay? And so now, what this basically tells us is that if x divided by r is equal to y divided by r, then this also means that x is equal to y. Or if we want to write it the way that we normally do, y is equal to x. And so as a rectangular equation, we just have the line y is equal to x. And of course, that goes along with what we've just drawn here, because our slope of our line is a positive 1 and our y-intercept is located at the origin. So it makes total sense. And so this example is trying to show you that anytime that we give a polar equation that is in terms of just an angle equaling some number, then know that in this case, this is going to be equivalent to a line with either a positive or a negative slope going through the origin in a rectangular sense. Okay. So, and again, when we go to our fourth video and we talk about graphing polar equations, this is one of the ones that we're going to have to know how to graph in general. So basically saying theta is equal to some number, we know based upon what that angle is, it's either going to be a line with a positive slope or a negative slope going through the origin. Okay. All right. So let's move on to our next example here. All right. So for our next example, it's very similar to the previous example that we've done, but notice now the angle has changed. Okay. And I'm going to graph this one just to kind of give us a frame of reference here. So notice here that 5 pi over 3, since pi over 3 is 60 degrees and 60 times 5 is 300, this is equivalent of saying that we want all the points that's going to be on the polar axis that aligns with the angle 300 degrees. So we know that the terminal side of 300 degrees is going to be in quadrant 4. So this line that I'm drawing here, and I'm going to overlay it in brown, this line that I'm drawing here is essentially the line that describes all the points that are on that equation. Okay. Now, for us to figure out what this is going to be here, one of the things that we note is that we have several points that are on here. Okay. To make life easy for ourselves, what we can do is just select a point, since we got several to choose from, to help us figure out what's going on. So since I know this is 300 degrees, this angle here is in quadrant 4 and it's 300 degrees. I know that this reference angle here is going to be 60 degrees. and I can form a right triangle here. Okay. And let's just say, based upon that, I know this is a 30, 60, 90 right triangle. This side should be square root of 3. This side should be 1. That side should be 2. So this point that I'm looking at, I'm going to choose the point 1 comma negative square root of 3 for that. And again, it's negative because in quadrant 4, I have positive x coordinates, negative y coordinates. Okay. So now that I have that, notice that I know 2 points that is on this particular line here. I know the point 1 comma square root of 3, and I know the point 0, 0. Okay. So what this tells me here is that I have enough to find the equation of a line. Now, since we have the point 0, 0, we know that our y-intercept for this line is going to be at the origin. Okay. So all I need to do now is figure out what is going to be the slope of the line. Well, that's just a change in y values over the change in x values. And of course, the change in y values is going to be negative square root of 3. Let's try to write that a little better. So change in y, negative square root of 3 to 0, over change in x, which is 1, 0, which is simply just square root of 3. So our answer in terms of rectangular coordinates will just be y is equal to negative square root of 3x. Okay. And so, of course, we use that by using y equals mx plus b. We know that b is 0 here, and we just found that our slope was negative square root of 3. And that is our answer. And so we see that the actual equation of the line that we came up with has a negative slope, and that makes sense based upon what we were talking about here, because our line is going down from left to right. So of course it should have a negative slope. All right, so for our next example, we're going to look at something that is not so easily to recognize or easily to get to. So we really are going to have to do some converting and algebraic manipulation to see what's going on there. So for here, we know, of course, that cosine could be represented as x divided by r, since we know that x is equal to r cosine theta. And of course, we can divide both sides by r to get that. Okay. So therefore, in this case, we know r is equal to 3 minus 2x divided by r. And I'll just write it like that. Okay. And so at this point, what we can do here is multiply both sides of our equation by r. And if I do that, I'll have r squared here, 3r there, minus 2x there. Okay. Now, at this point, what we can do is we know that r squared is just x squared plus y squared. So I can go ahead and fill that in. And of course, I know r is just going to be square root of that. So what I'll have here is x squared plus y squared is equal to 3 times square root of x squared plus y squared. And then this will be a minus 2x. And so technically at this point, again, this is in rectangular form. So this is an acceptable answer at this point. So I'm going to go ahead and box it off. Oftentimes, though, what we do, since we have this minus 2x hanging here, we'll add that to the other side, and we'll do the whole completing the square thing to get this side looking a little nicer. So I'm going to continue on and do that here. And I'll just put here acceptable answer. And again, the reason why I would want to go further, it kind of depends upon what I'm using this for, okay? All right, so also I can add 2x to both sides. And I know here that I'm going to have to do the whole completing the square thing. So we'll do this. So notice I'm adding 2x to both sides. And then here I'm introducing 1 times some number to both sides here. So I'm going to have to do the same thing over here. Okay. And if I do the whole completing the square thing, we know that we just have 2, this number here divided by 2 squared. And that's going to be the same thing there. And of course, all that will just equal 1. And I know that x squared plus 2x plus 1 is just going to be x plus 1 quantity squared. And here, this will just end up being 1 there. And so this is another acceptable way to write this particular answer here. Okay. Now, it depends upon your instructor or the application that you're actually using this for to be able to figure out which one is the better one to use, but both are correct. Okay, so for our next example, we have r is equal to 9 divided by sine theta minus 4 cosine theta, all in the denominator there. And we want to start off by recognizing again that sine theta can be expressed as y divided by r, and that cosine theta can be expressed as x divided by r. And so if we do that, then of course this could just be y divided by r, this could just be x divided by r. And what we have here is r is equal to 9 divided by y over r minus 4x over r. Okay. And if we work on the right-hand side sum, we know that this would just be 9 divided by y minus 4x, all of that over r. And that could also be rewritten as 9 over 1 times r divided by y minus 4x. Okay. Thus, we have r is equal to 9r divided by y minus 4x. So from here, we could kind of do the same thing as we did before in dividing both sides by r. What I'm going to do instead, just to kind of make this look a little different, is cross multiply. If I do that, then I end up having this. And then I'll go ahead and divide by r. And this will just be equal to y minus 4x is equal to 9, because these r's will reduce to 1 here. Okay. And so you can see here that now we have this in rectangular form. And if I was to add 4x to both sides, I would just have this equation of a line here. And so we have an equation of a line that is that has a positive slope, and its y-intercept is below the x-axis. And because of that, what we see here is with polar equations of this type, where we have some number divided by some difference of sine and cosine, like how we see here. What this translates to is a line that either has a positive or negative slope, but the y-intercept is not going through the origin, okay? And so that was very different than one of the earlier examples that we had, where we were just looking at the, let's say the angle theta is equal to pi over 4, or the angle theta is equal to 5 pi divided by 3, where we know that that would be a line that either has a positive or negative slope and it's going through the origin. So that's the difference in between the two there. And so again, the last thing that I want to say before moving on to our next example here is that notice that I was able to divide by r again. So to know that, I have to know that r is not able to be equal to 0. And of course, we know it's not able to be equal to 0 because in the numerator here, notice that we just have a number. So there's no way for us to get 0, because the only way r could be 0 is if the numerator was 0 and the denominator would be something else other than 0. So that's not possible. So we knew that we could divide by r in this case because we knew r cannot be 0 based upon what it was defined to be. All right, so let's move to our next example. So this next example here will be the last example of the type where we're taking a polar equation and we're trying to convert it into a rectangular one or a Cartesian one. The next set of examples that we'll do will be going opposite. We're going to take something that is in rectangular form and translate it into polar form. So I saved this example for last because we need to have a little bit more knowledge than what we did for the previous examples, mainly because notice that we're dealing with the difference of angles for a cosine function, okay? And so because of that, one of the things that's going to actually help us to be able to figure out how to write this in rectangular form is to use the addition formulas for cosine, okay? And specifically speaking here, we need to take note that cosine of A minus B is going to be cosine of A times cosine of B plus sine of A sine of B, okay? So this portion here, we could rewrite that way. And so because of that, that lets us know here, and I'm just going to go ahead and write it up here, that cosine of 2 pi over 3 minus theta is going to be equal to cosine of 2 pi over 3. Let's try to write that again. 2 pi over 3 cosine of theta plus sine of 2 pi over 3 sine of theta, okay? And so what we want to note here is that for cosine, and I'll go ahead and write this down here, note that cosine of 2 pi over 3, that 2 pi over 3 is in quadrant 2, so that means that this angle, that the cosine of this angle is going to be negative. So we could look at this as negative of cosine of its reference angle, and the reference angle for 2 pi over 3, let's try to draw that better here. Yeah, for 2 pi over 3 is just going to be pi over 3. So you can look at it this way. And of course, using what we know about the 30, 60, 90 triangles, pi over 3 is the same thing as 60 degrees. So this is going to be the square root of 3 side. This will be the 2 side. That'll be the 1 side. So here we know that cosine of pi over 3 is adjacent over hypotenuse, which will give us a minus 1/2. And of course, sine of 2 pi over 3 is just going to be the same as sine of pi over 3, because sine is positive in quadrant 2. So remember, negative x values, positive y values. And so sine of pi over 3 is just 3 pi over 2. So now that we have that, I now know here that cosine of 2 pi divided by 3 minus cosine theta, that's just going to be, here we have minus 1/2 cosine theta here, plus, and then 3 pi over 2 sine theta there. And so now that we have that, then of course, we could rewrite what we have here. So r cosine of 2 pi over 3 minus theta equals to 5. That implies here that we just have a negative r divided by 2. Or I'm going to write it this way. So negative r cosine theta divided by 2 plus square root of 3 r sine theta divided by 2, and that is equal to 5. Okay. So at this point, we're pretty happy because of the fact that we know that r cosine theta is just another way of saying x, and r sine theta is just another way of saying y. So here we know that all of this is just another way of saying x. This is another way of saying y. So therefore, what we have here is a minus x squared plus square root of 3. Sorry, a negative x divided by 2 plus square root of 3y divided by 2 is equal to 5. And if I was to multiply both sides of my equation by a negative 2, well, sorry, let's not do negative 2. Let's just do positive 2. If I do positive 2, then what I would get here is a minus x plus square root of 3y, which is equal to 10. And so now we see that this is starting to look really nice. And if I wanted to solve this for y, I would see that what I essentially would have here is an equation of a line again. And of course, to do that, the first thing I would need to do is to add both sides by add x to both sides, rather. That would be x plus 10. And then I would want to divide both sides by square root of 3. And this would end up being y is equal to x divided by square root of 3 plus 10 divided by square root of 3. And as you can see, that is just a line with a positive slope. Slope being 1 divided by square root of 3. And its y-intercept is going to be located at the point 0, 10 divided by square root of 3. So this would be your answer for that. All right, so we're done with our examples of taking polar equations and converting them into rectangular ones. So now we're about to do the reverse of that, which is deal with some rectangular equations and convert them into polar equations. All right, so for our next set of examples, since we're converting our equations from rectangular or Cartesian coordinates into polar ones, we kind of have to set the stage for how we want these polar coordinates to be expressed. And so we see here that r is basically going to be non-negative, and we're going to use standard angles for these examples. And in this case, these standard angles will be in degrees instead of radians like how we did before. So again, the standard parametric conversions apply. We know that x is equal to r cosine theta. We know y is equal to r sine theta. Of course, r squared is equal to x squared plus y squared, which means that square root of r is going to be equal to square root of x squared plus y squared. And we know here that we could use this particular equation, tangent theta is equal to y divided by x, to figure out what our angle would be if we needed to figure that out. Okay. All right, so for this first example, this one is relatively simple because of the fact that we know that x is just r cosine theta. So here we would literally just replace x with r cosine theta, and that would equal 4. Okay, and here there's really not much else we can do with that. Okay. If you remember, x equals to 4, if we graph that, is a vertical line. And so that vertical line would look something like this. Let me go ahead and graph it right quick. So it looks something like this. And so here, the reason why our r and our theta is not something specific, because this point here, and let's say this point here, both of these points have different values of r. Okay, we can't necessarily say that the distance from here to here is the same as the distance from here to here. Okay, so because of that, we know r is going to vary based upon the points that are on this line. Also, we know that the angle from here to here is different than the angle from there to there. Okay, so again, the angles are going to vary as well. So all the points that are going to be on this vertical line here are not going to have a specific value of r, not going to have a specific value of theta. So that's why we kind of have to leave it in general, like how you see it there. Okay. All right, so let's move on to example 2. So for example 2, we have our rectangular equation, y is equal to x times square root of 3. And so again, we remember that y is going to be equal to r sine theta. And we know that x is equal to r cosine theta. Okay. So if I was to actually go and substitute that in here and here, then what I would actually have is r sine theta is equal to r cosine theta times square root of 3. Okay. Now, in this case, if we assume that r is not going to be allowed to equal 0 here, then we can do some things. Note that if r is equal to 0, then what that basically does is that it puts us at the origin. Okay, so letting r equal 0 is going to be the equivalent of saying let x and y both equal 0. Okay. There's not anything interesting there, and we're not going to be able to find out any information from that. So to make life easier on ourselves, we're going to assume that r can't be 0 and then see what the equation looks like, and just notice that whenever r is 0, it's just going to be the point at the origin. Okay, so if r, so I'm going to assume here that r cannot be equal to 0 in this case. If I assume that, then what I can do here is divide both sides of this equation by r to get rid of it. And so therefore, if I do that, then I'll have sine theta is equal to square root of 3 cosine theta. Okay. And so now, notice that we have a trigonometric equation here that we need to solve. And this one is relatively easy for us to solve. And I could do that by dividing both sides by cosine. So if I did that, I would have sine divided by cosine is equal to square root of 3. And that would just be the same as tangent theta, because sine divided by cosine is tangent. And that would be square root of 3. And I'm just going to put it over 1. Okay. Now, with this equation here, note that we could draw right triangle here to kind of figure out what theta is going to be. Notice that square root of 3 and 1 are both positive. So we can assume that this is in quadrant 1. And since square root of 3 is the side that is opposite of theta, we know that in this case, theta is going to be 60 degrees. Okay. And if I remember correctly here, yeah, we said that we're doing everything in degrees. So what this lets us know here is that theta is going to be 60 degrees. Okay. So now that we know that, then we know that any point that's going to be on this particular line here is essentially just going to be on the line polar-wise. That's going to be the polar axis defined as theta is equal to 60 degrees. Okay, because that's the one thing that's in common with everything. And of course, if I was to draw that, that would look something like this. And I'm going to do this here for a second. So that line would look something like this. Okay, where this is, of course, the angle between here is 60 degrees. And radially, or on this polar axis, this would be the polar axis for 60 degrees here. So every point would meet that. I have a hole here because we assume that r cannot be 0. But again, if r was able to be 0, then that just translates to x and y both being 0. And they're both equal to 0 whenever this thing crosses at the origin. And so we had to kind of eliminate that to kind of see what everything else would do, and then we just fit it back in. Okay. And so we see here that based upon this equation, what r was really didn't matter in this case. Okay, because this equation kind of describes all the points that is on this line here. All right, let's move on to the next example. Okay, so for this next example here, this one is relatively easy. So we're going to take two different approaches here. So the simplest approach is, if we remember, since r is square root of x squared plus y squared, that tells us that r squared is equal to x squared plus y squared. And if that's the case, all of what we see here is just r squared. So simply put, our polar equation here would just be r squared is equal to 4. Okay. So that is the simplest approach that we can take for this. Now, the other approach I wanted to take is that, if you remember, what we're actually looking at here in terms of conic sections is we are looking at a circle whose center is the origin and its radius is 2. Okay. And so because of that, what we could do is we could also substitute in x to be our cosine theta, or in this case, 2 cosine, 2 cosine theta, and y here to be 2 sine theta. And so if we did that, what we would end up getting here is r is equal to 2. And of course, if we squared both sides, r squared would be equal to 4. Okay. There's no need for us to actually plug all that stuff in, just letting you know that since this is a circle, I could plug in r cosine theta here, r sine theta there, and work it out, and I would still get this answer here. Okay. And that's because if I was to plug that in, this would be r squared cosine squared theta plus r squared sine squared theta. And that would be equal to 4. We would factor out the r squareds. And then notice here that sine squared plus cosine squared, that's just equal to 1. Okay. And so you see that we would still end up with r squared is equal to 4 either way. But remembering that r squared is just x squared plus y squared allows us to be able to get to this answer faster. Okay. All right, so let's move on to the next example. So this next example here, we are going to need to use the parametric definition for x and y in terms of polar coordinates here. So we know x is equal to r cosine theta. We know y is equal to r sine theta. Okay. So here, this would mean that we have r cosine theta, quantity squared, equals to 4 times r sine theta. R squared cosine squared theta and then we have 4r sine theta here. All right, so now that we are at this juncture here, we need to kind of do some algebraic rearranging to get this to look nice. So the first thing that I'm going to do is to just divide both sides by cosine squared. So if I do that, then I'm just going to have r squared on the left-hand side, and I'll have 4r times sine theta over, and I'm going to split up the cosines here. I'll do it like that. And this will actually just be 4r times tangent theta times secant theta. Okay. Now, at this point, what we can do here is assume that r is not going to be equal to 0 again, because, of course, if it is, then that means that x and y are both going to be equal to 0, and that's just going to make this whole thing just turn into 0 equals 0, which is kind of trivial. So, and we already know that that can happen. So we're just going to assume that r can't be 0 so that we can divide both sides by r in this case. So if I do that, I'm just going to go ahead and kind of implement it this way. Then what we see is we have r is equal to 4 times tangent theta secant theta. And that would be it. And so, yeah, that would pretty much be it. And of course, you could leave this answer, and I'll kind of write it like this. So in this way, we're assuming that R can't be 0. Or you could leave the answer like how we had it. And assume that R can be 0. Okay. So let's say R equals to 0 is possible. Now, in reality, R equaling to 0 is possible both in this case too, but we just made this assumption so that we could get this result here. Okay. So what I'm basically trying to say here is that both of these answers are correct. So this is just a more simplified version of it. And to get there, we just assumed that R couldn't be equal to 0 to do it. Okay. And so we kind of need this because notice here that if R is equal to 0 here, we have to guarantee that there's some angle that's going to make this expression on the right-hand side equal 0 as well. And that's not easily done. But of course, if we said if R is equal to 0 here, then R is equal to 0 there, and it kind of zeroes everything out regardless of what these angles are. So again, it just depends upon, in this particular situation, if it makes sense to consider R is being equal to 0 or not. Okay. And that will depend upon the application. If you're just trying to give an answer for this particular problem, let's say you're in a normal math class or whatnot, this is probably the safest answer. But this is an acceptable one if you're allowed to assume that R is not equal to 0. So for our next example here, notice that the equation that we are dealing with here is an ellipse. And so what we're basically trying to do in this example is to figure out, well, how does an ellipse look if we expressed it in polar form? And so for here, what we'll do is just use what we know with X and Y, substitute the parametric definitions of X and Y in polar form accordingly. And then we're just going to algebraically manipulate what we can here. Okay. So we know that X is going to be R cosine of theta. And of course, since that's squared, that's going to make R squared and cosine squared. That over 9. And we'll do the same thing with Y. Y is R sine theta. And since that's squared, then it means R is squared and sine is squared. That's going to be over 4. And then we have that equal 1. So at this point, not much else we can do other than kind of get rid of these fractions here. So we could multiply both sides by 36 because 36 is a common factor of both 9 and 4. Well, least common multiple. Let me say it like that. Yeah. So if I do that, then this will give me on the left-hand side, 36 divided by 9 is 4. So that will be 4R squared cosine squared theta. And 36, if I distribute it to the other term, 36 divided by 4 is 9. That will be R squared sine squared. And this will be equal to 36 over here. Okay. So at this point, we pretty much have, at this point, we can actually say that this is the answer, but there is a little more simplification that I can do here. So I'm going to try to do that right now. And what I can do here to try to simplify this a little bit more is notice that 9r squared sine squared theta can be broken up into 5r squared sine squared theta plus another 4r squared sine squared theta. Okay. And here, what we need to recognize is that this 4r squared cosine squared theta and this 4r squared sine squared theta, that combines to just be 4r squared. Because if we wrote these together, we could factor out the 4r squareds there, and we would just have cosine squared theta plus sine squared theta. And of course, cosine squared plus sine squared, that's just equal to 1. So we could take this next line here and just rewrite this as 4r squared plus 5r squared sine squared theta and have that equal 36. And so here we know that either this answer or this answer is acceptable. Okay. I'll say both acceptable. And again, it just kind of depends upon what you need to do here. Of course, I could factor out an extra, r squared and kind of have 4 plus 5 sine squared theta in there. I could split this up and have this as 4r squared plus another r squared sine squared theta. I could do all that, but at that point, it really just does depend upon what you're actually going to be using the equation for to figure out what that best form would be. All right, so this concludes the third video in this video series of dealing with polar coordinates and equations. So the fourth and final video will get into how to graph polar equations. And I know that I'm going to be showing a lot in that video. So kind of like this one where I had a lot of examples and it was kind of long. That other one was going to be that way too. But just know that I'm going to try to get through the material as efficiently as possible. But it is a lot of little stuff that I have to show. So if you're going to be watching that fourth video and you know it's probably going to be about an hour as well, and hey, I'm going to need to kind of break it up, just kind of be prepared for that and plan accordingly. All right, I'll see you in that fourth and final video.